Hello, good evening. Hello, good evening. Welcome to the 10th week lecture tutorial session of applications of power electronics in power systems. I shall share my screen now. I hope you were able to see the screen. Am I audible? Hi. Anupam, can you confirm whether I am audible?
Yes, ma'am. Yes, ma'am.
Okay, okay. And can you see the screen now?
Yes, ma'am.
Okay, thanks for confirming. Welcome to the 10th week tutorial session of power electronics applications in power systems. So in the last class, we discussed about different applications of TCSC, like how we do the reactance control in TCSC and the operating principle of TCSC, all these things we discussed. So today the main topic of discussion will be harmonics in TCSC and the various applications of TCSC and its advantages over SVC. Earlier we talked about SVC in detail, how we operate SVC, what are the advantages, what are the disadvantages. So today we will discuss this for TCSC and we will see that TCSC has some advantages over SVC. So this we already discussed what is TCAC in the last session. So just for a brief recap, I have added this diagram. So this is the full form is thyristor controlled series capacitor. So obviously the capacitor will be in series with this with the line, and in shunt there will be a controlled reactance. And how do we control the reactance? The inductive reactance by placing these thyristors. So basically there is a fixed capacitor and there is a controlled reactor. So overall the combination will give us a variable reactance, right? So that could be inductive reactance, that could be capacitive reactance based on in what mode the thyristors are being operated, whether they are off, whether they are fully on, or they are conducting partially. So based on that, this net impedance will be decided. And the simplified diagram is this one, where we just represent this whole thing by a variable reactor with this arrow. This we discussed in the last tutorial session. Yeah. So the point is that when we do Varnier control, what is Varnier control? Varnier control is that mode of control when the thyristors are conducting partially. That is what we call Varnier mode of control. So in that mode of control, some harmonics are generated. Why? Because, okay, I will see whether I have added that figure. Yeah. So if you just see this figure, here this is the circuit basically. So this black waveform here, this is the line current, which is IT. This is line current, and then this pink waveform is the TCR current. Why it is why the shape is like this? Because obviously the thyristors are being controlled. The firing angle we are varying. So for some portion they are not conducting, and for some portion they are on. That's why we get this kind of current, discontinuous current. Now simply apply KCL at this node. If you apply KCL in this node, what will you get? This line current is the sum of ICT and ITCRT, right? So this current has two paths, one through the capacitor, another through the inductor. And this diagram basically represents capacitive mode of control. Why? Because if you remember in the last session we discussed that in capacitive mode of control, the TCR current, this current is in the opposite direction to the line current. So that's why their directions are, when this is positive, the inductor current is negative, and when it is negative, the inductor current is positive. So in this case, what will be the capacitor current? The capacitor current will be something like this. If you just apply KVL, right? So it will be something like this. Now you can easily understand this current is obviously not sinusoidal. And if the current through a capacitor is not sinusoidal, then obviously the voltage across the capacitor will not be sinusoidal. The voltage is like this one. This voltage contains a fundamental component at power frequency and some harmonics, right? So this is for capacitive mode of control. And when there is inductive mode of control, that is the net impedance is inductive. The net impedance is positive. In that case, the line current and the inductor current are in the same direction. In that case, the capacitor current, this red one, is like this. In this portion, it gets subtracted and the current is something like this, and the voltage is something like this in green. Here also there are harmonics, right? So all these harmonics we get due to the partial conduction of the thyristors. Okay. Yeah. So yeah, so the expression of the voltage across the capacitor is like this. So this is the voltage. Im is the peak of the current. Okay. So this is the peak line current basically, and Xc is the reactance of uh, reactance of the fixed capacitor. Okay, and lambda we already discussed about lambda. So lambda is basically omega r by omega. Omega r by omega, where omega is the power frequency and omega is the resonant frequency. This expression we already got when TCR is conducting, right? This is when TCR is conducting. And when TCR is non-conducting, in that case ITCR is 0, then the expression of the voltage is something like this. And there is a constant VC dash, and VC dash we can write like this. This is time invariant. This whole thing, IMXC by lambda square minus 1, and this whole thing, this is only dependent on beta, but there is no expression of time. So this is time invariant. So we got two equations based on whether the TCR is conducting or the TCR is non-conducting. Now, once we have the expression of this voltage, what we can do to analyze what are the harmonics? Obviously, we will do Fourier transform, right? Fourier series. We will represent this in terms of a Fourier series. Okay. We will do FFT. And that will give us the harmonics. So VC1, this is the peak of the fundamental. This is the peak value of the fundamental component that is present in the capacitor voltage. And the expression is 4 by pi 0 to pi by 2 VCT sin omega t d omega t. And this we can divide in two portions, obviously, when the TCR is conducting and when the TCR is non-conducting, right? And we will get this big expression over here. And ultimately, we will get this expression after simplification. Okay. Yeah. So this is the expression. So Xc is the I already told Xc is the reactance of the capacitor, capacitive reactance, and XL is the inductive reactance. Okay. XL is the inductive reactance. Now, if we want to just find out what is the net impedance, ZTCSC, that will be simply VC1 by IM. Why? Because VC1 is the peak of the fundamental and IM is the peak of the line current. So just divide the voltage peak by the current peak and you will get the net impedance. Okay, the effective impedance seen by the line. So this is the expression. Here in the expression, you just have to uh, just put Im in the denominator here and you will get the expression. And again some simplifications are done here. And finally, and here again, there is some modifications. So finally, what we get this expression. Okay, we get this expression. And if you divide by Xc, the reactance of the fixed capacitor, then the expression is this. So the derivations are done in the lecture. You can go to the lecture by Professor Sanjeev Ganguly and you can see how the derivations are done step by step. Okay. So what are the things that we are seeing here? First of all, we need to know what is beta, and then lambda we obviously know. Okay, lambda we know, and beta value if we know, we will be able to find out what is this ZTCSC. Okay. Yeah. Okay. So let's go to the questions. Which of the following application of TCSC is used as a modular level control in power system? So as I told, TCSC has various applications. So one table is given here for better understanding. So there are two types of control. One is common level control and one is module level control. Okay. So this is common level means this is done to all the modules, all the TCSC modules. So by common level control, what we do, power scheduling control, power swing damping control, transient stability control, and subsynchronous damping control. Power scheduling control means by, as we already saw for SVC, by controlling the TCSC impedance, we can change the steady state power transfer, right? By controlling the TCSC, we can increase the power transfer capacity. Okay, so that helps in power scheduling control. Then damping. So TCSC provides damping to power oscillations. So that is another application. And then transient stability and subsynchronous damping. So subsynchronous damping means the when the oscillation, the frequency of oscillation is less than the power frequency. That is called subsynchronous oscillation. Okay. TCSC can provide damping for that also. And then there comes module level control, which we use for reactance control, then synchronous damping control, bypass protection. Bypass protection we already discussed. Bypass protection is when we bypass the TCR. Okay, we bypass the TCR. And then there are line over current, arrestor over current, energy protection. So what is the modular level control? That is reactance control. Okay, reactance control. So next question. Which of the following control application of TCSC maintains a constant power in the line parallel to the TCSC compensated line? Okay, so there are two types of control. The first one is constant power control. This is constant power control where a constant current is maintained in the TCSC compensated line. Okay. So if this is the control range from here to here, then the IREF is constant. As you can see, the current is constant. And this is the control range based on these two different slopes. This slope over here, this has the lower slope compared to this slope. So here because this is del I by del V, it represents, the slope represents del I by del V. Therefore, in this case, the ZTCSC is maximum because here the slope is the lowest. ZTCSC maximum. Okay. Maximum. For this one. And for this one, ZTCSC is minimum. Okay. Between these two, this is the between this range, you can control the current at a constant value. So this is constant power control, and there is another control which is called constant angular difference control. Okay. In that case, what happens? There is a line parallel to the TCSC compensated line and constant power is maintained in this line. Okay. So the TCSC controlled in such a way that constant power is maintained in this line. So as constant power is maintained, that means that delta is constant, obviously, right? Delta is constant because the power is a function of this angle delta. That's why this is called constant angular difference control. Okay. So here also you will get some range, and in this range you can maintain this constant power in the parallel line. Uh, so TCSC maintains a constant power in the line parallel to the TCSC compensated line that corresponds to constant angular difference control. Okay. The third question, harmonics in TCSC is generated when? So we just discussed that when there is a partial conduction of the thyristors. In that case, the harmonics are generated. Okay. So the thyristors conduct partially. In that case, harmonics are generated. Yeah. So this diagram I explained. That this is in capacitive mode. This diagram is for capacitive operation. Capacitive operation. Okay. And this is for inductive mode of operation. Yeah. Okay, the next question. Consider the following statements regarding TCSC. TCSC with inductive Vernier control can increase the steady-state power transfer capacity of a power transfer line. In inductive Vernier control, the net reactance is positive. So this is basically R here. This is R. TCSC with inductive Vernier control can increase the steady-state power transfer capacity. That is the first statement. Second statement is in inductive Vernier control, the net reactance is positive. Here, this one in inductive Vernier control, the net reactance is positive. That is true. Because when there is inductive control, the net reactance is positive, right? That's why the TCR current is in phase with in the same direction as in the line current. Okay. But the first statement tells that in inductive Vernier control, the steady state power transfer capacity can be increased. That is not true. Why? Because, so I have explained it here. So suppose this is a TCSC compensated line. Okay. Suppose the TCSC is not here. Suppose there is only the transmission line and there is no TCSC, right? So this is V delta and this is V angle 0. In that case, what is the steady state power transfer? The steady state power transfer is V square by X, where X is the reactance of the line sine delta, right? That is the power transfer, sine delta. But when there is TCSC, right? In that case, okay, in that case, the power becomes, so P compensated PC is equal to P square by X minus say TCSC, okay? Say TCSC. And then there will be sine delta. Sine delta. So this additional term ZTCSC comes And obviously you can understand that if ZTCSC and this minus sign comes only when the operation is capacitive, right? In that case, the denominator is lower than simply x. Okay, the denominator is lower, that's why TC is higher than P, right? So P compensated is higher than P only when the operation is capacitive. Therefore, the right option is that A is false and R is true. Okay, R is true. Okay, till this point, is it okay? Okay, so let's go to the next question. Which of the following is true describing TCSC in comparison to SVC? A TCSC should always be placed at the midpoint of the transmission line to increase the power transfer capacity. Option B is an SVC with a lower rating can achieve an equivalent enhancement in power transfer capacity compared to the TCSC. Third option is a TCSC with a lower rating can achieve an equivalent enhancement in power transfer capacity compared to the SVC. And the last option is the cost of SVC is higher than TCSC of equal rating. Okay, so what is the correct option? Now, while studying SVC, we saw that we always used to consider that the SVC is placed at the midpoint, right? That's what we always considered. So the effectiveness of SVC is maximum when it is placed at the midpoint, okay, like this. But for TCSC, that is not the criteria. You can place the TCSC anywhere and you can get the same advantages. Okay, you can get the same compensation. So the first option is not correct. Should always be placed at the midpoint. That is not applicable for TCSC. That is applicable for SVC. An SVC with a lower rating can achieve an equivalent enhancement in power transfer capacity compared to TCSC. No, that is not true. The correct option is a TCSC with a lower rating can achieve an equivalent enhancement in power transfer capacity compared to the SVC. Okay, so that is one advantage of TCSC over SVC, that a TCSC with a lower rating can achieve an equivalent enhancement in power transfer capacity compared to the SVC. Okay, that is the correct option. Okay. So the next question. A TCSC is said to be operated in inductive mode if, so the TCSC operates in inductive mode when? So okay. So you know that the angle of advancement beta, it can vary from 0 to pi by 2. Okay. It can vary from 0 to pi by 2. When beta is 0, that means that indicates that the thyristors are fully off. And when beta is pi by 2, that means the thyristors are fully on. Okay. When the thyristors are fully on, what we get? We get just a fixed capacitor and the inductor, fixed inductor. Okay. Because now there is no control in the thyristor, they are just fully on. So just like that, right? And when the thyristors are fully on, then we get the inductive mode of control. So the angle of advancement is, when the angle of advancement is pi by 2, in that case we get the inductive mode. Okay. Okay. So please excuse me if there is some additional sounds. Actually, uh, uh, I am not in the institute right now. I am traveling, so that's why you may get some additional sounds. Just excuse that. So the next question is, consider the following statements regarding TCSC. So there are again two statements. The first one is, in the event of power system abnormality, if mechanical power exceeds electrical power, TCSC operates in capacitive mode. The next option is, the negative impedance in capacitive mode increases the electrical power. Okay. So, uh, in the application of TCSC, we saw that it contributes in damping the oscillations, and it also contributes in extending the transient stability. Okay, it improves the transient stability. So the first statement states that in the event of power system abnormality, if the mechanical power exceeds electrical power, TCSC operates in capacitive mode. Okay. So that is true. When the mechanical power is greater than electrical power, TCSC operates in capacitive mode in that case. And the second one is, the negative impedance in capacitive mode increases the electrical power. So obviously we already saw, right, that when the TCSC operates in capacitive mode, the electrical power increases, the power transfer increases, right? That's why uh, option A is right. Both A and R are true, and R is the correct explanation of it. Okay. So the electrical power increases when the TCSC is in capacitive mode, and the electrical power decreases when the TCSC is in inductive mode. So P increases when TCSC is in capacitive mode of control, capacitive mode, and the electrical power decreases when the TCSC operates in inductive mode, right? Inductive, inductive mode. Okay. Okay, so I will take a 10-minute break, and then I will resume the rest of the problems. Okay, so let's resume the discussion. Okay, so question 8 to question 10, they are common data question. So this question says that a TCSC is placed at the midpoint of the transmission line. The reactance of the fixed capacitor and the TCR are, sorry, there will be ohm. So 250 ohm and 10 ohm respectively. This is the reactance of the fixed capacitor and this is the reactance of the TCR at power frequency, that is 50 Hertz. Determine the value of angle of advance at which the resonance occurs. Okay. Okay. So basically it is given that XC is equal to 250 ohm. 250 ohm. Okay. This is 250 ohm and XL is equal to 10 ohm at 50 Hertz. Okay. So the first thing that we need to do is we have to find out lambda, right? We need to find out lambda. What is lambda? Lambda is omega r by omega, right? Now omega we already know omega is equal to 100 pi because the power frequency is 50 Hertz. So power angular frequency will be 2 pi times 50. 2 pi times 50, that is 100 pi. Right? So this is equal to omega n and this is equal to omega c. This is equal to omega c. So we know what is omega r. Omega r is basically root over of 1 by root over of LC. That is the resonant frequency by omega. So this is basically 1 by omega root LC. Okay. Now, if you just put the omega inside the square root, then it becomes omega square. So we can write it like this. This is omega L multiplied by omega C, right? Because omega we have put inside the square root. So what is this? This is so this is XL by XC, right? Because XC is what? XC is, sorry, uh, here I have written it wrong. So this is wrong. So XC is 1 by omega C. This is 1 by omega C and XL is omega L. Okay, inductive reactance XL. Okay. and just we can write it like xc by xl. So this is xc root over of xc by xl. Xc value we know, xl value we also know, right? 250 and 10. So this becomes root 25, that is 5. So we got the lambda value as 5. Okay. They have we need to find out what is the angle of advance, that is the beta value. We need to find out the beta value during resonance condition. Okay. Now when resonance happens, in that case xl at omega r, okay, xl at omega r is equal to xc at omega r, right? The inductive reactance and the capacitive reactance, their magnitudes are same at resonant frequency. Okay, at omega r. And here we are talking about parallel resonance because the inductor and the capacitor, they are in parallel. The capacitor and the inductor, they are in parallel. So in case of parallel resonance, what happens is the net impedance ZTCSC, ZTCSC, ZTCSC becomes infinite. Okay, ZTCSC becomes infinite. Why? Because you just, so this is omega r, this is omega r L, and this is 1 by omega r C, right? So if you just represent it, you should represent it minus j by omega rc, and this is j omega r in. Okay. Now if you find out the equivalent impedance, then what we will get? I will just take uh one slide, extra slide to so just let's. So what will be the net impedance over here? The net impedance will be ZTCSC will be what? Is equal to J XL minus J by XC by J XL. This is multiplied and this is minus J by XC. So they are equal, this and this. So this is infinite, okay. And when ZTCSC is infinite, when beta is equal to pi by 2 lambda, okay. 2 lambda. And the derivation is done here, okay. In the lecture notes, you will get the derivation. Here I have included that. So basically, yeah, so this is the expression of ZTCSC. Okay. Now, if you see here, you will see an expression of 10 lambda beta and 10 beta, right? So this expression we will get. So 10 lambda beta. If this is equal to pi by 2, then say TCSC will be infinite. Okay. If this is equal to pi by 2. Sorry, this is equal to, so lambda. So if lambda beta is equal to pi by 2, because then 10 lambda beta will be infinite. So beta is pi by 2, pi by 2 lambda. Okay. So beta equal to pi by 2 lambda. So the correct option is pi by 10 because lambda is equal to 5. Okay. Okay. So the next question. Determine the expression of instantaneous voltage across the capacitor when the TCR is non-conducting. Okay. When the TCR is non-conducting. So we will just get the expression when the TCR is non-conducting and try to find out. Okay. I think here I have written it, yes. So let's see. So this is the expression. Okay. So this part is the expression when TCR is non-conducting. Okay. So yeah, just a minute. So I will just take one clean slide. Okay. So what is the voltage expression when TCR is non-conducting? The voltage expression is this. Okay, this. And what is VC dash? VC dash was also given. VC dash is equal to this one. Okay. So this is VC dash. This is the expression of VC dash, right? Okay, now what we need to find out is just replace the values. Okay, just replace the values. So first we can find out what is VC dash. IM we don't know, but we don't know. We know what is the value of XC. That is 250. It was given 250. Then IM, and what was lambda? Lambda was 5. So lambda square minus 1 will be 24, right? And here we have sine beta plus 5 cos beta, 5 cos beta, then tan 5 beta. Tan 5 beta. This is PC dash. And then after that we have this part. So what is the final expression? The final expression is 250 Im by 24 minus sine beta plus 5 cos beta, then tan 5 beta. After that we have 250 Im, 250 Im and in bracket sine. What is omega t? Omega is 100 pi, so sine 100 pi t. 100 pi t minus sine beta again. Minus sine beta. Right? So you see here 250 Im is there, here 250 Im. So we can take common. 250 Im we can take common. And then this will be 1 by 24 this part. And then and here it will be sine 100 pi t minus sine beta. Okay. So let's see which one we are getting. So the first expression is 1 by 24 5 cos beta, then tan 5 beta minus 25 sine beta plus sine 100 and pi t. So here just a minute. Yeah. So here just take 250 Im common and then it is 1 by 24 minus sine beta plus 5 cos beta tan 5 beta then sine 100 pi t minus sine beta. Right? And you can further simplify by taking this and this because both of them are have sine beta. So this will be so minus sine beta minus 24 sine beta, so minus 25 sine beta, and 1 by 24 will be out. Okay, so I think the first option is correct, but you can also verify by yourself. I think this is the correct option. Okay, the first option. Okay, the 10th question. Determine the net reactance of the TCSC during fixed capacitor mode of operation. So this is already given in the question that during fixed of capacitor mode, the reactance is 250 ohm. Okay, in ohm. So this is 250, option B. All these are in ohms. In ohms. In ohms. So option B is the correct option. Okay. Yeah. So I hope you understood the questions. If you have any query, you can ask me in the next tutorial session. Okay. Thanks for joining the session. We will meet in the next Saturday.